Alright, well, how much fun are we having now? So much. In this video, we're going to be talking about our third way to solve first-order differential equations, which is called the exact equation. So this is yet another special form, I suppose we could say the exact differential equations. This is another special form, just like separable ones and linear ones. This is the exact differential equation. If you ever find a differential equation that is in this form, that is an exact differential equation, then this method will apply. And in this video, I will show you the general method to solve it, and also how to test if a differential equation is an exact form, because it's slightly more complex than testing if it's linear or testing if it's separable, but it is doable. Now, an exact differential equation is one that we'll often see written in slightly different form than we've seen previously. Instead of combining the dy's and dx's into the derivative, we're going to write it in differential form. I believe that I brought up differential form in one of the videos, maybe on separable differential equations, but the differential form is just the form where we have some function of x and y, so p of x and y, times the derivative with respect, not the derivative, the differential of x. These are called, a very important distinction is that these are called differentials, so they're not derivatives. They are those infinitesimal changes we're always talking about in calculus. These are differentials, which actually is where the differential of equation from differential equations comes from, which is kind of cool. So we have p of xy times dx plus another function, q of x and y times dy, this equaling 0. So if you have an equation in differential form such that you have your function of x and y times dx plus your another separate function of x and y times dy equaling 0, then your equation might be an exact form. And this is key. Not every differential equation of this form is exact. So it might be exact. And this might is very important. And in order to show you how to test whether this differential equation is in exact differential equation, I'm going to take a brief sidetrack, brief tangent here, to something called a total differential of a two-dimensional function of two variables, which is a brief foray into multivariable calculus. We'll do fine though. So if we have a function f of x and y, just any old two-dimensional function fx and y, we can define its total differential to be the d f of xy is equal to the partial derivative of f with respect to x times dx plus the partial differential of f with respect to y times dy. And you might notice this is fairly similar to if we had just taken the derivative of f of x and y with respect to x. So just showing how we get to this. This is called the total differential. This is the total differential that I just wrote down. Total differential. Showing how you might get to this, what you can do is you can say, okay, what if we took the derivative of f and x, and we can remember that this is truly just y of x, playing hide and seek there, with respect to x. Well, this is the multivariable chain rule, so we would get, okay, how fast is f going to change when you change its x component times how fast the x component is changing, which is dx over dx. And then we're going to have, okay, how fast is f going to change when you change its y component, which is partial f partial y, times how fast is the y going to change. The y is going to change at a rate of dy dx. Now obviously dx dx, that's just 1. So this is going to be partial f partial x plus, this is all times 1, plus partial f partial y times dy dx. And the way we get it into this total differential form is by multiplying through by dx, so that we get the slightly interesting df is equal to partial f partial x times dx. You have to make sure you're not mixing up these partial x's and actual dx's because they're different, plus partial f partial y dy. And this is where you get the total differential form from. All right, so sorry for that little sidetracking. But okay, so first thing you might notice is that this differential form of our differential equations, so this looks fairly similar to this. Of course, what we're saying for the differential equation is that it must equal 0. So if, and this is the condition for being exact now, I'm giving it to you, if our differential equation p times dx plus q times dy equals 0, if this is an exact differential equation, there must be some two-dimensional function, f of xy, whose total differential is this left-hand side here, p dx plus q dy. Okay, let's unpack what that means. That means that there has to exist. So let's write it down here, that if p dx plus q dy equals 0, if this is exact, then, and we could also write this as if and only if, because it does go both ways. So if and only if p dx plus q dy equals 0 is exact, then there exists some function f of xy such that the partial of f of xy with respect to x, so partial f partial x equals p of xy, and partial f partial y equals q of x and y. If this is true, so if partial f partial x equals p of x and y, and the partial derivative of f with respect to y is q, then we say that this differential equation is in exact form. Now, that's fine, but what, are you going to go find a function of f that makes this true? We want an easier way to check if this is indeed an exact equation before we go looking for this f, because otherwise we might go on a wild goose chase. We'd be, okay, here's a differential equation. Is it in exact form? Let's try to find a function, but then it turns out it isn't in exact form, and you're just running around in circles trying to find a function that doesn't exist. So how could we possibly find if this is indeed an exact equation, but with an easier method? Well, we turn to yet another theorem in multivariable calculus for this. And the theorem we turn to is Klara's theorem, which, and I'm always bad with specific theorem names. I like to remember what they do, not what they're called. But for this case, let's also learn what it's called. It's Klara's theorem. And what it says is that if you have a function, multivariable function, that is continuous on some interval, then for that interval, the mixed partial derivatives will equal each other. So f sub x y, so the partial derivative of f with respect to x then y, is equal to taking the partial derivative with respect to y and then x. This is what Klara's theorem says. And we can see that it is useful because if indeed our equation is exact, then we would be able to rewrite it as the partial of, let's get a good color, so we'd be able to rewrite it as the partial of f with respect to x dx plus the partial of f with respect to y dy equals 0. So we have these two elements here, partial of f with respect to x, partial of f with respect to y, if it's exact. So if it is exact, we should be able to use Klara's theorem and say, okay, this p of xy, because this is P, this is Q. If we took the partial with respect to y of P, and we took the partial with respect to x of Q, if these two things were equal, then this would imply that there was another function, f, such that f, because remember, P is just f sub x. So we're saying if we're taking the partial with respect to y of P, that's f sub x y, that this is going to equal some other f sub y, because that's Q sub x. And indeed, Klara's theorem says that this must be true. So if there exists, this is a long way of saying that, if there exists a function whose partial derivative with respect to x is our p of xy, and whose partial derivative with respect to y is q of xy, then taking the partial of p with respect to y and seeing if it's equal to the partial of q with respect to x is sufficient to prove whether or not there is a function. And what we say is that if there exists some function f of xy for which partial of f with respect to x equals our p, and the partial of f with respect to y equals our q, we say if this is true, then the equation p of x y dx plus q of xy dy equals 0, then this equation is exact. And it took quite a long time to even just formulate what it means to be exact. In the next video, we're going to continue this theory and see, okay, now that it is exact, okay, great, how do we solve it? All right, I'll see you in the next video.